with unknown probability P of success. Or sorry, it's just a Bernoulli. So P to the X, 1 minus P to the 1 minus X. And we are looking at a random sample from this distribution, meaning that X1 up through Xn are IID Bernoulli P. So if we're trying to find the MLE of this, what is our first step here? Okay, so what we have here is the PMF, the probability mass function for one observation. But we need the likelihood function is the first thing we need. So how do we get the likelihood function from the mass function that we already have here? Okay, the product of what? The product of, here it's going to be f sub x of xi given p. And what is our product over? What values does it range over? Say that again, please. I'm talking about the product, though. What does our product start at and what does it go to? So it's going to start at I equals 1, and it's going to go up to. Because we're not always, but when we're looking at likelihood function specifically, it will start at 1 and go up to the sample size. So now we need to actually evaluate this. So we can put in our here product from I equals 1 to n of p to the xi times 1 minus p to the 1 minus xi. And how can we simplify this product here? Okay, so would it help if I split this up into here, the product from I equals 1 to n of p to the xi times the product from I equals 1 to n of 1 minus p to the 1 minus xi. Do you see what simplification we can do here? Distribute it how? We've got a product here that is the product of a bunch of things with the same base raised to certain exponents. So if we're multiplying things with the same base, how can we simplify that? Let's say I'm multiplying y to the a times y to the b. What is this equal to? Exactly. And we'll do the same thing here, even though that this is a product over n values rather than just 2. We can take this product and turn it into a sum in the exponent. So here we'll have p times the sum from I equals 1, or sorry, p to the power of the sum from I equals 1 to n of xi times 1 minus p to the sum of 1 minus xi from I equals 1 to n. But how can we simplify this exponent here? So if I'm looking at just this exponent here, I'm taking the sum of all of these values of 1 minus xi, and here I'm doing a sum over a sum. So I can distribute the sum inside if I want. That's just associativity. So I can say that this is the sum from I equals 1 to n of 1 minus the sum from I equals 1 to n of xi. But what is this thing here? The sum from I equals 1 to n of 1. This is going to be 1 minus, sorry, n minus the sum of xi summed from I equals 1 to n. Does this make sense? Okay. And what is our next step here? Okay, so this is all the simplification that we can do to the likelihood function, unless we want to. It can be useful to here say that the sum of the xi's from I equals 1 to n, that this is equal to n times x bar. Does it make sense why this is true? Yes, does it make sense why that's true? Well, I mean, we know that here, x bar, this is just defined as the sum of all of our observations divided by the sample size. And so that just gives us what we have here by multiplying by n on both sides. Does that make sense? Okay. And so the next step here that we have the likelihood function is to take the log likelihood, because that is, whenever you can take the log likelihood, the vast majority of cases, that's going to make it easier to maximize. Now, we didn't do that when we were looking at the maximum likelihood estimator for that uniform distribution, because that one actually we could not take the log. Or we could, it would not have been helpful to us for that particular one, because we wouldn't be able to differentiate. But here we're going to eventually differentiate to do a first derivative test to find the maximum. So we would like to take the log to make differentiation easier. And so we can define lowercase l of p given x as the log, which in statistics, if you see log, this is assumed to be the natural log unless stated otherwise. Log of this. And so then this is the log of exactly what we have up here. And how do we simplify this? Nx plus so it's not anything like simplifying the nx, it's applying the log function to what we have here. The nx bar will move around, but here I want you to think of this as the log of something times something else. And what is that? If I, for instance, have here the log of AB, how do I simplify that? Mm-hmm. And so this one gives us log, if we're treating this thing as A and this thing as B, that's going to be log of P to the nx bar plus the log of 1 minus P to the n minus nx bar. Okay. And now what property of the logarithm do we apply? So we've already used this one. What's another one that's useful to us? So it has to do with the log of, let's say, y to the a. This is equal to what? It's a times log of y. So when we have the log of something raised to a power, we can simplify by bringing that power down to the front of the distribution. Sorry, not the distribution, the front of the logarithm. Does that make sense? So then applying that property to what we see here, what will we end up with? So this is one of our exponents here, and this separately is another exponent. So what do I do with those to get them out of the logarithm? I can just bring them to the front, and then the p and the 1 minus p will not be raised to any exponents. So this is just n x bar log p plus n times nx bar. And I'm actually going to factor the n out as well, just so these are more similar. N times 1 minus x bar log 1 minus p. Do you have any questions about that? Okay. So now, this is about all the simplification we can do to the log likelihood. So now our next step is to take the derivative, because we want to do the first derivative test of this, so that we find the point where our first derivative is, sorry, our first derivative is 0, our second derivative is negative, and that indicates that our function has a maximum at that point. So what is the derivative of this one with respect to p? So let me ask you just in general for these derivatives of logarithms. If I'm looking at the derivative with respect to x of some function of a log of u, where u here is a function of x, what is this derivative? This will be, we traditionally write this as u prime over u, or in other words, the derivative of u with respect to x divided by u. So here it's not, we're not differentiating with respect to x, we're differentiating with respect to p. But we'll take the derivative of the inside of our log with respect to p, which is just 1. And it's going to be that over p and then times this nx bar out here still. So it's nx bar divided by p plus, applying that same sort of thing here, what is the derivative of this, the log 1 minus p? So the derivative of 1 minus p with respect to p, because we need our u prime here, that's going to be negative 1. So we'll have a minus here instead of a plus, times n times 1 minus x bar divided by 1 minus p. Does this make sense? So we're looking here at this. We want the derivative with respect to p technically partial derivative, but it doesn't make a difference, of n times 1 minus x bar log 1 minus p This stuff has nothing to do with P, so it can come out to the front. So we have n times 1 minus x bar ddp log of 1 minus p. And then this right here, we need to take the derivative of that with respect to p for the chain rule, because we need that u prime. And then we take the derivative of log of 1 minus p with respect to 1 minus p. And that's where the u prime over u comes from. So this is going to be equal to n times 1 minus x bar times -1 times 1 over 1 minus p. And that's what we have here in black. Does that make sense? Okay. So now, what do we do with this first derivative? Well, what we'll want to do here is, because we are looking to maximize or find the estimator for P that maximizes this likelihood function, we are going to set this thing equal to 0 and then solve. So let's type this. We replace P with P hat. That's just a notational change. Set the log likelihood derivative equal to 0, and then solve for P hat. So I'm going to say that the log likelihood derivative evaluated at P equal to, this is just changing the notation. There's nothing interesting so far. But the reason I'm doing this is because once I set this equal to 0, I'm now looking for a solution to this equation in terms of P. No, sorry, in terms of P hat. And that's my estimator. So I'm talking in terms of the estimator now. And now I want to solve this for P hat. So what is my first step to that? We're looking for the MLE. To find the MLE, we need to solve this thing for P hat. How should I do that? This is just a matter of algebraically solving this equation. There's no need to replace anything. All we're doing here is solving this thing for p hat. So we can add the 1 minus, or we can add this thing here to both sides. And we get nx bar divided by p hat equal to n times 1 minus x bar divided by 1 minus p hat. Does that make sense? Yeah, so our first step is just to add that to the other side. And then we are going to multiply by p times 1 minus, or sorry, p hat times 1 minus p hat on both sides, so that we get this going up here and this going up here. And so then we have n times x bar times 1 minus p hat equal to n times 1 minus x bar times p hat. Does that make sense? I just crossed multiply. Okay. So remember that I'm trying to solve for p hat here. So what is my next step? Yeah, so how do I get p hat by itself? I've got p hat factored out over here. I need p hat by itself over here. So I can multiply by the n x bar. I can distribute that, and I'll get n x bar minus n x bar p hat equal to and I can do the same thing over here, multiply, I'll multiply the n and the p hat in, so that I'm just expanding this whole thing. N p hat minus n x bar p hat. Does this make sense? Yeah, I just expanded this whole thing. And then what do I simplify in the next step here? So we've got a minus RP hat on both. Sorry? And so now we have nx bar equals np hat. We divide by n on both sides, and we have that p hat is equal to the sample mean. Okay, now we haven't shown that this is quite the maximum likelihood estimator yet, because we don't know whether it's a maximum or a minimum. We know it's one of those, local max, local min, but if we want to show that it's a maximum specifically, what do we do? We need to take the second derivative. So I'll take the second derivative of the likelihood function, the log likelihood, because we want to verify that the second derivative is negative. Because if the second derivative is negative, that means we have a maximum, that means that the vertex that we found here using that first derivative test is in fact a maximum. And so we just have to differentiate what we had up here. Well, technically this one up here, because we haven't put in p hat yet. But we differentiate that thing with respect to p, and we get negative nx bar over p squared minus n times 1 minus x bar over 1 minus p squared. And what can we say about this term here? I'm not comparing degrees here, and I'm not taking a limit. And like here we have an n, here we have a p to the second, so those are not comparable. What I'm trying to determine is whether this whole thing is less than or equal to 0, or specifically less than 0. So what can I say about this fraction here that's useful to that end? So I'm trying to find out if this whole thing is less than 0. Is the n greater than 0 or less than 0? Is n positive or negative? I'm talking about just n. N is positive. It's the sample size. Is x bar positive or negative or 0? X bar. I'm just talking about x bar. X bar is either 0 or 1. Or sorry, not 0, 1. X bar is either 0 or positive, and p squared has to be positive. So this whole thing, including the negative sign, has to be less than or equal to 0. Now this whole thing, including the negative sign, n is positive when minus x bar is either positive or 0. And if it's 0, then this has to be positive. So this would be less than 0. And 1 minus px squared is positive. So this whole thing, including the negative, is less than or equal to 0. And so this is less than 0 for all p, in fact, on our interval 0, 1. And so yeah, n is the sample size, so that has to be at least 1. X bar is the sample mean, and if all of the x's are either 0 or 1, x bar has to be between 0 and 1 inclusive. P is between 0 and 1 exclusive, so it is strictly positive. So the negative n times x bar divided by p squared has to be negative unless it's 0, which would be if x bar was 0. Now this one, the n is positive because it's the sample size. The 1 minus p squared is positive because p is positive. And 1 minus x bar is either positive, or if x bar was 0, then if x bar was 1, that would be 0. But in that case, this whole thing would be 0 and this whole thing would be negative. So one of these is going to be negative. At least one of them is going to be negative. If one of them is negative, the other one could be 0. But in any case, this whole thing is less than 0. And so I didn't even plug in p hat yet. That's just for any value of p. But that means that our second derivative evaluated at p hat is less than 0. So p hat equal to x bar is the maximum likelihood estimator. Does that make sense? Okay. we'll move on to looking at, is p hat an unbiased estimator of p? And what can we say about that? The expectation of p hat is just x bar. So this is the expectation of x bar. And what is the expectation of x bar for any distribution? There's no theta here. So any distribution at all, this is an important thing to remember. The expectation of x bar is equal to the expectation of x. Also, I don't think we need this one for this problem 1, but the expectation of s squared is equal to the variance of x. Those are very important things to remember. Okay, so this thing is equal to the expectation of x. And what is the expectation of x for this distribution? Remember, it's a Bernoulli distribution with mean p, with a proportion p. I just gave it away. It's equal to p. And this is something that you should remember, is that for a Bernoulli variable with probability p, the expectation is p. If you'd like, we can actually derive that, or we can continue on with this. Okay, so if we want to actually show why the expectation of x is p, the expectation of x is equal to what in terms of my density function? The density for that Bernoulli. But it tells it to you in the problem, and we were writing it earlier, but what I'm asking you is a fact that is true for any continuous distribution. How do we write the expectation of the distribution in terms of the density function? This is equal to the integral of x times the density of x evaluated or sorry, x times the density of x with respect to x. And this is over all real numbers. But for us here, our density function is equal to 0 outside of that interval 0 to 1. So we can write this as the integral from 0 to 1 of x times our density for x, which is p to the x times 1 minus p to the 1 minus x dx. Oh, I'm sorry. This is a I apologize. This is not a continuous distribution. So we're looking at a sum, not an integral. So we're looking at the sum over all possible x of x times, not the density, I misspoke, sorry. It's the mass function for our Bernoulli variable. And this is going to be the sum of x times p to the x times 1 minus p to the 1 minus x, for our only possibilities for x are x is 0 or 1. So here we have 0 times p to the 0 times 1 minus p to the 1 minus 0 plus 1 times p to the 1 times 1 minus p to the 1 minus 1. And so this whole thing cancels because it's 0. This thing is just equal to 1. And this thing already is 1 here. And so this is just equal to p. So what we've shown is that the expectation of p hat is equal to p. And so what does that allow us to conclude? It's what? What did you say about it? Yeah. So p hat equals to x bar is unbiased for p. Do you have any questions about that? Okay. Now part C, we want to find the maximum likelihood estimator of G of P equal to the probability that X equals 0. And what property can we apply to this one? What property of the maximum likelihood estimator lets us get a maximum likelihood estimator for this value? we're going to apply the invariance property. Yeah. Invariance property says that the maximum likelihood estimator of any, I don't remember if it has to be continuous or not, but we'll say any function of the any function of a distribution's parameter is the function evaluated at the MLE of the parameter. So in other words, for any function g, the MLE of g of theta is equal to g of the MLE of theta. So you just plug in the MLE for your parameter, and that gives you the MLE for g. Do you have any questions about that? Is it possible to what? Yeah, I can go for another hour. No, that's fine. We'll just keep going. Okay, so applying this invariance property here, what is the MLE of G of P? Using what I wrote in red, either the sentence or in the symbols, how can we find the MLE of this function of P? What do you mean by that? No? So the invariance property tells us that we don't need to do any of that because we can just plug in p hat for in place of p. So this is g of p hat. And probably the x is 0 is f of 0 given p. And so g of p hat is g of x bar is f of 0 given that this is x bar. And our mass function is the p to the x times 1 minus p to the 1 minus x. So we plug in x bar instead of p, and we plug in 0 for x. And so this is equal to just 1 minus x bar. Does that make sense? No, this is any MLE at all. We can take any function of any MLE, plug in the MLE for the parameter, and that gives us, or sorry, here's a little bit wrong. Any function of a parameter we're interested in, the MLE of that function is the function evaluated at the MLE of the parameter. And this is the same thing that we did in the examples that I had for you when we were looking at, like, with the uniform distribution, the expectation of x is what we were trying to estimate. The maximum likelihood estimator for that one was equal to theta over 2, or rather theta hat over 2. And that's because the expectation was theta over 2. So the MLE of the expectation is the MLE of theta over 2. Does that make sense? Okay. And this is all for question 1. Do you have any more questions about that? Okay. Do you mind if I go to the bathroom? Okay. Okay. So going on to number 2 here, we are given this particular distribution, which is actually a exponential distribution. And we're asked first to find the MLE beta hat of beta. What is our first step here? No, there's only one parameter. It's beta. X is the value of the variable. So the first step when finding the maximum likelihood estimator is always to find the likelihood function itself. And then for most distributions and parameters, take the log of the likelihood and differentiate. Does that make sense? And I'll say this is the maximum likelihood estimator of a parameter. So if it's a function of a parameter, like we just saw in 1C, we can just use the maximum likelihood estimator of the parameter, plug that into the function, and that gives us the MLE of the function itself. But when we are looking for the MLE of a parameter, we need the likelihood function to start with. So here we have a PDF, and this is the PDF, as we're used to, of a single observation from this distribution. And what do we do with this PDF in order to find the likelihood function? Mm-hmm. And so for my likelihood function, what should I write here? It is it's the product from I equals of my density for X across all of these values in my sample, all of those Xi's. And so then I can replace this with the actual density in terms of beta and X. So this is 1 over beta exponential of minus xi over beta. Does that make sense? Mm-hmm. Yeah. And now how do I simplify this problem? not taking a log yet. Let's start with how do we get this 1 over beta simplified? What can we do about that one? Okay, so we're taking the product of all of this stuff over all the values of n, but anything that is not dependent on n, we can just bring outside. So the 1 over beta is just, and so this is 1 over beta to the n, product of I equals 1 to n, exponential, and so on. And so then how do we simplify from here? I have a product of a bunch of things with the same base. So what do I do with the exponents to simplify? No, we're not taking the log yet. We can simplify this just using rules about exponents. We did this for problem 1 as well. So how do I simplify this using exponent rules? Mm-mm. So once again, we are applying the rule that we did before of y to the a times y to the b equals y to the a plus b. And that gives us that this is the exponential, which I'll switch to writing this as exp, of the sum of the xi's from I equals 1 to n divided by beta. And this is negative. Does that make sense? Say that again, please. Yes. Hmm. Yeah. Does it make sense how I got there, though? So this is as much as we can simplify this right now. So what our next step is to take the logarithm. Because when we go to find the MLE of this, we're going to take the derivative, and it's easier to take the derivative of the log version of this than it is to take the derivative of just what we see right there. So this is going to be, let's start with taking the log of this part. What does that give us? Yes. So I'm talking about the first thing here. We're looking at this as log of, whoops, need to copy it. Log of this thing. We once again have the log of a product. It's this thing times this thing. And so how do we split up that logarithm? Okay. So this is log of 1 over beta to the n plus, and we take the log of the exponential, and the exponential just disappears. So this is just going to be minus the sum of xi over beta. And now what can I do about this first term to simplify it more? Sorry, I need to let my dog in. Okay, I'm back. So how do we simplify this log 1 over beta to the n? Does it help if I write it as beta to the negative n? Okay, so then how does it simplify? Negative n log beta. Does that make sense? Okay. And so then we have the negative n log beta minus some xi over beta. This is as much as we can simplify the log likelihood. And so then what is our next step with finding the MLE? So the next thing is to differentiate the log likelihood function. Because we need to maximize this. And sorry, I was right. I've been writing x beta. This should be beta x. Because we consider the log likelihood and the likelihood to be a function of the parameter. And the data is a condition for the distribution, or sorry, not the distribution, for the function. But this is our log likelihood derivative is what we need to find next with respect to beta. So what do we have for this first term? The derivative of that with respect to beta. What's the derivative of n log beta with respect to beta? We were talking about the derivative of log before, so if we have like d dx of log of x This is 1 over x. If it's some function mu, u, this is u prime over u. So then what is this derivative? Okay, so it's going to be the negative n is just going to stay there essentially. Derivative of log beta with respect to beta is 1 over beta. So this is negative n over beta. And then the derivative of this with respect to beta, we can write this whole thing as negative sum of beta to the negative 1. And so what does that become? Oh, sorry, I forgot the xi. So it's going to be positive sum of xi over beta squared. Does that make sense? Okay. And now what do we want to do with this? How do we want to use this first derivative? What was that? This use, are you saying how to get from here to here? Okay. So our next step we can do here, if you want, we could do the second derivative, but we want to take this and set it equal to 0. Because we need to find the value of beta hat that makes this equal to 0. And so we can add n over beta hat to both sides. And this gives us that the sum of xi over beta hat squared, write it this way, n over beta hat is equal to the sum of xi over beta hat squared. Does that make sense so far? And then we can multiply by beta squared on both sides. So you have n beta hat squared rather, is equal to the sum of the xi's. And so beta hat is equal to sum of the xi's over n, which is x bar. Does that make sense? So we haven't shown yet that this is the MLE. Because what thing do we need to do next? We haven't shown yet that it's the MLE. Well, we've determined that x bar is the solution to the derivative of the log likelihood being 0, but we haven't determined whether this is a maximum or minimum yet, technically. So what we need to do next is take the second derivative to determine whether x bar is a minimum or maximum. Does that make sense? Yeah. So second derivative of our log likelihood with respect to beta, and we can evaluate it at beta hat. This is going to be positive n over beta squared, beta hat squared. And the other one is going to be negative sum of xi's over beta hat cubed. Does it make sense why that's the second derivative? A 3, yes. Because this was a squared in the denominator, so this was the sum of xi's times beta hat to the negative 2. And actually, this should be a negative 2 here, not a negative 1. And so we bring the negative 2 out front, and we reduce the degree on beta hat. And so beta hat goes from beta hat to the negative 2 to beta hat to the negative 3. Does that make sense? Yeah, so the this is coming from the power rule. Which says that the derivative of x to the a with respect to x is equal to a times x to the a minus 1. That's all we're doing here. Because here, in this first derivative, this term is, we can write it as beta hat to the negative 2 times the sum of the xi's. And so we've got negative 2 times beta hat to the negative third times the sum of the xi's. Does that make sense? Okay. And now we need to decide whether this thing is positive or negative. We want it to be negative. And so this one, it actually benefits us to plug in the x bar. And so beta hat being x bar, we can call this n over x bar squared minus 2. And the sum of the xi's, like we said in the last problem, is equal to n x bar over x bar cubed. Simplify this. This is n over x bar squared minus 2n over x bar squared. And so this is negative n over x bar squared. N is positive, x bar is positive. We have a negative out front, so this is less than 0. And so, what can we say about beta hat because of that? No, we're not talking about bias here. Why were we interested in the second derivative? Why were we interested in the likelihood function at all? Because well, we're looking for the maximum likelihood estimator, so the value that maximizes the likelihood. The second derivative being being less than 0 rather, means that our likelihood function has a peak, has a local maximum at beta hat. And our bounds for the possibilities of beta are everything greater than 0. So we don't have any endpoint to check. So that means that this local maximum that we found has to be the global maximum for this variable, because it is has a derivative of 0, and the second derivative is negative. And we don't have any other local extrema. So beta hat is the MLE for beta. Does that make sense? Okay. Next, we want to know, is beta hat an unbiased estimator of beta? And so first, when we're doing this, what is a reasonable question to ask about beta hat? So a natural thing to do first is to find the expectation of beta hat. And so what can we say about that expectation? Yeah, because it's the expectation of x bar, which is the expectation of x. And then how do we find the expectation of x? We take the integral. Did I write dx before? Oh, sorry, there should not have been a dx there. There's no dx for sums. That's just an integral thing. But yeah, we're taking the integral technically from negative infinity to positive infinity of x dx. But this particular density function is 0 for values of x less than or equal to 0. So we can just write this as the integral from 0 to infinity of x times 1 over beta e to the negative x over beta dx. And I'll write this as x over beta. What is the antiderivative of this thing? So antiderivative is the same thing as the indefinite integral. So we're looking for the function that has this thing as its derivative. We know that the derivative with respect to x of e to the u is u prime e to the u. Or if you want to write it in the version that doesn't include the chain rule, you would need to do the chain rule separately for this one, but it's d dx. E to the x is just e to the x. And we're trying to apply this backwards. So here we have e to the u it's like the negative x over beta. So that means that we can write this as negative u e to the u. And here u prime is equal to derivative with respect to x. So u prime is 1 over beta. And so this is this one is this one we have to do integration by parts for. So yeah, we'll still use what we had in red, but we'll do integration by parts. And for integration by parts, the way we can write this is that the integral of u dv is equal to uv minus the integral of v du. And for us here, we can take let's say we'll choose we want I think the dv to be the transcendental. So we'll choose if it doesn't work out cleanly, we can just go back and switch it. Choose u to be x over beta, in which case du and v is dv is e to the negative x over beta du. Oh, sorry, no. Dx. And so then v is equal to negative beta e to the negative x over beta. And du here need more space. du is equal to 1 over beta dx. So that means we can write this as the integral of u dv, which is uv minus integral of v du. uv is x over beta times negative beta, which is negative x, e to the negative x over beta, evaluated from x equals 0 to infinity, minus the integral of negative, it would be negative beta e to the negative x over beta times 1 over beta dx. So the 1 over betas would cancel. I'll just write it here as negative beta over beta, e to the negative x over beta dx, evaluated from 0 to infinity. And then what happens with this is we have negative infinity e to the negative infinity over beta. The transcendental decays faster than the linear term. So that's going to be 0 in a second. Minus negative 0 e to the negative 0 over beta. And that's going to be 1. And I actually will just go ahead and simplify this now to, this is just plus. And it's going to be plus negative beta e to the negative x over beta, evaluated from x equals 0 to infinity. And anyways, this thing goes to 0. This thing goes to positive 1. This thing is going to go to negative. That's going to be 0 plus oh no, and this one is there's still 0 here because we're multiplying by 0. Yeah, okay. So that's 0. And so this is just beta. And remember that this was the expectation of beta hat. So what we've just shown is what? What about it? Yes, it's unbiased for beta hat is unbiased for beta. And that's part 2. Do you have any questions about that? Okay. So we're at 2 hours now. Do you want to keep going with this, or do you want to stop here? I can go till about 10:30 your time. Okay. Let's yeah, sure. We can finish 2 and then start on 3 if you'd like. So part 3 of question 2. We want the MLE of G of beta equals the variance of X. So for this, what do we need to do in order to find the variance of X? Or how can I write an expression for the variance of X? We'll write this as the expectation of X squared minus the expectation of X quantity squared. So expectation of X we already found. That's just beta. And then for the expectation of X squared, how do we get this thing? So similarly to how we found the expectation of X by integrating the density function times X, we can find the expectation of X squared by integrating over the whole real line X squared times f of X dx. Is that familiar? Okay. So that's going to look very similar to what we had up here. And the difference is that we're just squaring, oops, it should be this one. The difference is that we're just squaring X. So X gets a square on it. And we are looking at a similar situation as before of needing to do integration by parts. So I'll just copy down the integration by parts formula. And here we can choose let's see, we chose before dv was equal to e to the negative x over beta dx. And so v was the integral of that with respect to x, which was negative beta e to the negative x over beta. U is x squared over beta. Du is going to be 2x over beta dx. We write this as the integral from 0 to infinity of, oh, sorry, not the integral yet. It's just going to be uv, which is x squared over beta times negative beta e to the negative x over beta, which is negative x squared e to the negative x over beta. Evaluated from evaluated from x equals 0 to infinity minus the integral of negative beta e to the negative x over beta times 2x over beta dx. And this first one is going to end up as 0. Because here negative infinity, that's decaying to 0. And we plug in 0 for x there, and we're going to get 0 as well for that. So that's just 0. And then this one simplifies to plus 2x e to the negative x over beta dx. And this looks very familiar because this is just, this is from 0 to infinity. This is just beta times the expectation of x. Or rather, 2 beta times the expectation of x. Where's beta coming from? Or where's the 2 coming from? I don't feel like there should be a 2 in there. I know it's coming from the derivative of the x squared over beta. Oh, no. This is fine. This is fine. Because we're not looking at the variance yet. We're just looking at the expectation of x squared. So this thing here, because this is equal to beta times the expectation of x, that's where we get this. And so then this is 2 beta squared. And so our variance is equal to 2. I'm just going to copy this down again from up here. Is that it was the expectation of x squared minus the expectation of x quantity squared. That variance is going to be 2 beta squared minus beta, which was our expectation of x squared. And so this is beta squared. Does that make sense? Okay. So this is the variance of x. This is the variance of the exponential distribution with parameter 1 over beta. And we're looking for the maximum likelihood estimator of the variance of x. And so what can we say to get that maximum likelihood estimator? No second derivative. We don't need to get the derivative of anything. We're going to apply a property that we've talked about before. This is the invariance property. So we can say that by the invariance of the MLE for the variance of x and I'll write it as g of x, or sorry, g of beta is g of beta hat, which is just beta hat squared. Because g of beta is beta squared. And we're done with that one. Do you have any questions about that? Okay. So I think that's actually a good place to stop for today. Do you want to set up another session to talk about the last problem? Okay. We won't be able to finish it, but do you still want to start with it? Okay. So here, this is just working with a Oh, this is our log normal distribution, actually. But we're asked first for the MLE of sigma squared. And so what is our first step? First step to finding MLE should be very quick for you right now, by now. Mm-hmm. So we're taking the product from I equals 1 to n of what? Mm-hmm. Yeah, so this is f xi. So we're evaluating it at observation given sigma squared. And that's this whole thing again. Just with the xi's. And now how do we simplify this? Okay. So yeah, we can bring, yeah, so we'll take our 1 over 2 pi sigma squared, and I'm writing the sigma squared inside the square root because this is, since we're looking for the MLE of, well, if we had the MLE for sigma, then we could just square it. But the reason I want to find the MLE for sigma squared directly is because that will avoid us having to use the chain rule for this one. And so then this is the product xi to the negative first. And if we're taking the product of the exponential, remember that this as the exponential of the sum of these things. So exponential negative 1 over 2 sigma squared, sum from I equals 1 to n of log x squared. Does that make sense? No log yet. The reason it's a summation is because this is, yes, because it's in the exponent. When we write exponential of whatever you want, exp of y, this means e to the y. we just express it this way to make it easier to read on the page. And so now we have this. This is actually all we can do here, unless you want to write the -1 outside. Might be a little bit cleaner, but yeah, really this is all for the likelihood function. And then the next thing we need to do, because we want to differentiate this, and differentiating something with a product in it is very impractical, we're going to take the log of it. So we're looking at log likelihood of sigma squared given our sample is the log of our likelihood function. And so that's the log of everything that we have above. And what does that log come out to? Yeah, and we really have 3 parts of this. So we have this one, we have this one, and we have this one. So we can split this into 3 separate logarithms. And so what is this first thing? Oh, let's just write them separately first. So log of 1 over root 2 pi sigma squared plus log of product of xi's to the -1st plus, and then this one, the exponential goes away because we're taking the log. So this one is just 1 over 2 minus 1 over 2 sigma squared sum of log x squared And now how do we simplify this? Starting with that first term, what are here, since the numerator is 1, it's easier to just express this as the log of 2 pi sigma squared to the -1/2. So if this is 2 pi sigma squared to the -1/2, how do we simplify this one? So this is another application of log of y to the a is equal to a log y. And so this is going to be negative 1/2 log of 2 pi sigma squared. Our next thing, same deal. Minus log product of the xi's. And then this thing here stays the same. And there's one more thing that we can simplify to this. Do you see it? No, the power of 2 is outside the log for that one. I'm looking at the middle term. What do we do about the middle term for that one? The product. And what do we get instead? No, so this is still just an application of the log of products as the sum of the logs. So this is minus the sum of the log xi's. Does that make sense? Okay. And so this is our log likelihood. And I do need to stop here, but the rest of this procedure is just like before. We would differentiate with respect to our parameter of interest, which is sigma squared. Find where that's 0, and assuming we can find somewhere that it's 0, check the second derivative of the log likelihood and make sure that that is negative. Do you have any questions for me? Okay. So I will later today put the whiteboard in the Google Doc. Do you want to set up another session now? Okay, on Wednesday? Okay. Okay, so 8 o'clock on Wednesday then. Okay. And how long do you want to meet for? Okay. Well, I'm just saying, like on Wednesday, how much time do you want? Okay. So 1 hour Wednesday. Bye, Yusuf. Have a good one.